Good afternoon, students. So we will start our live lecture of real analysis.
Yes, ma'am.
In previous session, we have seen upper bound, least upper bound, examples, and then lower bound, greatest lower bound, and examples, right?
Yes.
Yes, ma'am.
So any difficulty in that?
No, ma'am.
Yes.
No, ma'am.
Also, we have proved that if a is equal to open interval 0, 1, then least upper bound of a is equal to 1 as well as GLB of a is
GLB.
0. Okay, now we will go to completeness axiom. Completeness axiom. Today we will see Archimedean property. Archimedean property. So before that we will require completeness axiom. Okay, whether screen is visible?
Yes, ma'am.
Yes, ma'am.
Yes.
Yes, ma'am.
Okay, so
Yes,
now
ma'am. Yes, madam.
what is completeness axiom? First we will write that. Completeness axiom. What this axiom says that any non-empty subset A of real line A of R with an upper bound has least upper bound. What this axiom says that if you take any non-empty subset of real line which is bounded above or which has an upper bound, it will have least upper bound. Is that okay? This axiom, this is very important axiom. It is called as completeness axiom. Any non-empty subset, for example, you take open interval 0, 1, which is bounded above, whether it has an upper bound.
Yes, ma'am.
Yes, so it has a least upper bound also, we have proved it. So whichever non-empty subset of R, if it is bounded above, then it will definitely have a least upper bound. Okay, this we will require to prove our Archimedean property, and the Archimedean property or Archimedean principle, which is again a powerful principle, important principle in real analysis. I will state that one, Archimedean property. APB, in short we write Archimedean property. We will write as a theorem. What it says that if x comma y belongs to R, any two real numbers with x greater than 0. Take any two real numbers with one real number is strictly greater than 0, then what this Archimedean property says that there exists natural number n belongs to n such that nx strictly greater than y. Can you see this property?
Oh, yes.
What requires x and y, any two real numbers with x greater than 0, positive real number, then there must exist a natural number satisfying the property nx greater than y. Okay, so we will prove this proof. What is given here?
Real numbers.
X comma y.
Given x comma y belongs to R with x greater than 0. Whenever we want to prove some theorem, first think of what is given and what we want to prove. What is our claim? What we want to prove. Okay. So here what is given? X and y belongs to R with x greater than 0. That is given. And what I want to prove? What is my claim? What is my claim?
Nx greater than y.
Nx is greater than 1.
We want to prove existence of a natural number satisfying this property. Existence of a natural number n satisfying nx greater than y, right? This property. So what is my claim? We want to prove there exists a natural number n belongs to n such that nx is greater than y. So how we will prove? Suppose my claim does not hold or my claim is not true. Suppose there does not exist. Many times we prove with contradiction. Okay. On the contrary, whatever we want to prove, you assume on the contrary there does not exist a natural number such that nx greater than y. Means what? Suppose there does not exist n belongs to n such that nx greater than y. That is what it means. For every natural number nx is what? This property fails now.
Less than y.
Nx is less than or equal to y, right?
Right.
This property for every natural, there does not exist natural number means for every natural number n this property fails. Nx greater than y fails means what? Nx is less than or equal to y, negation of this, right?
Yes.
So that is
Yes.
for every for every natural number n belongs to n, nx is less than or equal to y, right? So what I want to prove? I want to arrive at some contradiction, right? For all n belongs to n, nx is less than or equal to y. So let a is equal to nx such that n belongs to n. What can I say about this set, which is a subset of R? This a is a subset of R because n is a natural number, x is a real number. Nx must be a subset of R. Yes?
Yes, sir.
Whether it is a non-empty set? clearly A is a non-empty A is a non-empty set. Non-empty set and bounded above also.
Yes, ma'am.
And A is a non-empty set and A is bounded above. Why it is bounded above? Why it is a bounded above subset of R? What is the upper bound? When we say that A is bounded above, if it is an upper bound. What is an upper bound for this set A?
Plus infinity.
P infinity plus infinity.
No,
X is greater than 0.
no. I am saying what is an upper bound for the set A. A is my nx. N belongs to N. What I am having here?
Y is upper bound.
Y is an upper bound because for every natural number n belongs to n, we are saying nx is less than or equal to y. Right? So y is a real number satisfying nx is less than or equal to y. Every element of this set A. Y is greater than or equal to every element of this set A. Right? So y is an upper bound. You can write here since y is an upper bound. Upper bound of A. Okay, so I am having a non-empty subset of R which is bounded above. So by completeness axiom, what can I say? What is my completeness axiom? Any non-empty subset A of R with an upper bound has least upper bound. Right? So my this A also must have a least upper bound. Therefore, by completeness axiom, by completeness axiom, A must have least upper bound. Say alpha. Okay, that is alpha is equal to LUB of A. So we are denoting that least upper bound by alpha. Is that okay?
Yes, ma'am.
Okay. Now alpha is least upper bound. So what can I say? Therefore, for this implies nx is also less than or equal to alpha for every n belongs to n. Alpha is least upper bound and it is least. Since it is upper bound, nx is less than or equal to alpha for all n belongs to n.
Yes, ma'am.
Yes. Now,
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
can I write like this? N plus 1 of x or not of x into x is also less than or equal to alpha because n plus 1 is also a natural number.
Yes, ma'am. Yes, ma'am.
Yes.
ma'am.
So this implies nx plus nx plus x is less than or equal to alpha for all n belongs to n. So what this implies? Nx is less than or equal to alpha minus x for all n belongs to n. Is that okay?
Yes, ma'am. Yes.
So what can I say about alpha minus x?
It is equal to 1.
It is an upper bound for the set A. Alpha
Yes,
minus x, because what is the nx? I will write properly. Nx is less than equal to alpha minus x for all n belongs to n, means what? Alpha minus x, that is alpha minus x is an upper bound for the set A. Am I right?
Yes, ma'am.
So what? Alpha minus x is an upper bound for the set A. But what is alpha?
Ma'am, alpha,
Yes.
ma'am, alpha minus x upper bound कसा होईल मॅम?
इथे बघा फ्रॉम
कारण
दिस
की अल्फा आपण लीस्ट अप्पर बाउंड घेतलेला आहे ना आणि त्याच्यातून जर एक्स मायनस करायला म्हणल्यावर ते अप्पर बाउंड होणार नाही.
yeah, but what we are getting here? We are getting here alpha minus x is an upper bound, but alpha is the least. So which must be contradiction, because alpha is the least, right? That only we want, no? Why we are getting like that? Because our assumption is wrong. What is our assumption? We are assuming that for all natural number n, nx is less than or equal to y. We are assuming this. Due to this, we are getting that contradiction, right? Are you getting this? Alpha, this, or we will say the instead of the, that is, I will write this implies. We are not, we are getting from our calculations. Nx is less than or equal to alpha for every natural number. So n plus 1 is also a natural number. So we are getting n plus 1 into x is also less than or equal to alpha. So nx plus x is less than or equal to alpha. So this implies nx is less than or equal to alpha minus x for all n belongs to n. But this implies alpha minus x is an upper bound for the set A. But alpha is least upper bound. Therefore, alpha must be less than or equal to alpha minus x, which is contradiction, to alpha minus x is strictly less than alpha, right?
Yes, ma'am.
Or instead of like this, which is contradiction, since alpha minus x is strictly less than alpha as x is strictly greater than 0. अल्फा मधून आपण पॉझिटिव्ह व्हॅल्यू मायनस करतो, सबस्ट्रॅक्ट करतोय, राईट? सो इट मस्ट बी स्ट्रिक्टली लेस दॅन अल्फा, which is contradiction. Is that okay? Therefore, our assumption is wrong, and hence, which is contradiction. Therefore, there must exist a natural number satisfying therefore there exists n belongs to n such that nx is less than or equal to y. Is that okay?
Yes, ma'am.
So this is the Archimedean property. Now we'll go to another version. Lemma say set of natural numbers n is not bounded above. This is another version of Archimedean property. What we want to prove now? N is not bounded above. That is, for all x belongs to R, there exists, for all x belongs to problem, for all x belongs to R, there exists n belongs to n such that what? N is not bounded above, we want to say. What should be relation between x and n then?
Is greater than.
Less than.
Less than or greater than? We want to show n is not bounded above. So you give me any real number, I will give you a natural number which is greater than that real number, right? So it should be less than. Is that okay?
Yes, ma'am.
Set of natural numbers is not bounded above, I want to say. Then if you say 3.5 is a real number, I will give a natural number which is strictly greater than that 3.5. 4, 5, any natural number you can give. Is that okay?
Yes, ma'am.
So
Yes, ma'am.
that we want to prove. Means we can easily see, but we have to prove as a mathematical steps. Okay. So how can I prove using completeness axiom? Again we will use completeness axiom. Okay. So what should I do? Suppose on the contrary assume that n is bounded above, right? And then we will arrive at a contradiction. By contradiction we will prove this. Okay, most of the proofs we will use method of contradiction. Okay, so suppose n is bounded above. Bounded above means what? Bounded above means what? That is,
Upper bound.
there exists x
Alone.
belongs to R such that n is less than or equal to x for all n belongs to n, right? There exists a real number such that any which will be greater than or equal to every natural number, because we are saying n is bounded above. Is that okay?
Yes, ma'am.
Yes.
Yes, ma'am.
So again we are saying, so n is a non-empty set which is bounded above. So by completeness axiom, what can I say? Therefore by completeness axiom, n must have, what n must have?
List of
A
Least upper bound.
least upper
Least upper
bound.
bound.
Say alpha. Say alpha. So what this implies? N is strictly less than or equal to alpha for all n belongs to n, right?
Yes, ma'am.
So what this implies? N plus 1 is also less than or equal to alpha for all n belongs to n. N plus 1 is also a natural number.
Yes, ma'am.
So I am getting this. Again, what can I say? N is less than or equal to alpha minus 1 for all n belongs to n. So what this implies? What can I say about alpha minus 1? Same thing whatever we did in previous Archimedean property proof.
Is so list upper bound.
Alpha minus 1. No, alpha minus 1 is upper bound na, for set of natural numbers. Alpha from this step. From this step, I can only say that alpha minus 1 is an upper bound for set of natural numbers, right? Alpha minus
Yes, ma'am.
1 is,
Yes, ma'am.
is an upper bound for set of natural numbers. But what? But alpha is least upper bound of n, which is contradiction. Which is contradiction, because we are getting again contradiction, since alpha minus 1 is strictly less than alpha. Is that okay?
Yes, ma'am.
Yes, ma'am.
Yes.
Yes, ma'am.
Okay, so we have proved one version of Archimedean property. What is? Take any two real numbers with one x greater than 0, then there exists a natural number n such that nx is strictly greater than y. And also we have proved that set of natural numbers is not bounded above. Now we want to prove, or we will first write, this is as a remark we will write. The above lemma is also one of the version, or the above lemma is another version of, also known as version of Archimedean principle or property. Okay, so if somebody asks you state and prove Archimedean property, you can prove that set of natural numbers is bounded above, is not bounded above, that also, or another earlier one also, x and given any two real numbers with xy belongs to R with x greater than 0, then there exists a natural number n such that nx is strictly greater than y. Okay, now we want to prove these two versions are equivalent. Next theorem.
मॅम
Yes.
मॅम असंच होल नंबरच्या बाबतीत पण असू शकतं का?
Whole
जसं
number.
आपण नॅचरल नंबरला प्रूव्ह केलं.
तिथे एक minute. Okay, so now we will prove next theorem. Prove that, don't say as a theorem, we can do. If we are saying as a theorem, we won't try to prove that both versions of Archimedean property are equivalent. We want to prove now these both versions of Archimedean property are equivalent to each other. Equivalent means 1 implies 2 and 2 implies 1. That is statement 1 and statement 2. What is our statement 1? Let xy belongs to R with x strictly greater than 0, then there exists natural number n belongs to n such that nx is strictly less than y. Sorry, nx is greater than y, no? Nx is greater than
Yes,
y.
ma'am.
This is statement 1, and what is statement 2? What is statement 2? N is not
Not bounded.
bounded above. We want to prove these two statements are equivalent to each other. So what is our claim? 1 if and only if 2. Statement 1 if and only if 2. So suppose 1 holds. Statement 1 holds. So suppose how we will prove this? To prove, first we will write first implies one implies 2. So let xy belongs to R with x greater than 0. And what I want to prove? I want to prove n is not bounded above. Okay. So can you think of the proof? So assume, on the contrary, assume n is bounded above, right?
Yes, ma'am.
So how can I prove now? One, let xy belongs to R with x greater than 0. Then there exists natural number n belongs to n such that nx is strictly greater than y. So for particular x is equal, x and y are any real number with x greater than 0. So for particular x is equal to 1, what will happen? In particular, for x is equal to 1, what I am getting?
N is greater than 1.
There exists natural number n belongs to n such that n is strictly greater than y. X is equal to 1 we are saying. So n is strictly greater than y means what? Y is a real number. N is not bound. This implies n is not bounded above. No need to go use contradiction and right.
Yes, ma'am.
Yes. Now on now to prove 2 implies 1. Now suppose n is not bounded above. And prove that there exists for n is not bounded above. Let xy be x comma y be real numbers with x greater than 0. And now I want to prove there exists a natural number n such that nx is strictly greater than y. So now here you can use contradiction. Here you can use contradiction. How can you prove this? Can you think of a proof?
Then y.
Plus.
We suppose nx is less than y.
Y.
Then equivalent to each other. Is that okay?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So any doubt in this?
No, ma'am.
Okay, so tomorrow we will see density of rational numbers, or we can have no. Okay, tomorrow we will see that. Okay, so for today this much is enough.